We're going to work out the critical points, well, it's only a point, of this Gaussian function, and we're going to classify it. So when we work out critical points, whether we're looking for minimum, maximum, or saddles, we firstly need to know where the tangent plane is 0. That is, where f sub x equals f sub y, so the first partials with respect to x and y, where they're simultaneously 0. So let's differentiate f of x to find those simultaneous equations. That's going to become a plus because we get a minus from there. So we got to do the function of a function rule, right? Derivative of exponential is just itself, but then we're differentiating this argument up here, right? And that's going to give us minus 2x in this case. Similarly for y, I mean, you can just take the shortcut here and notice that x and y are pretty much interchangeable. And you find that. Now, we obviously want to solve these simultaneously. You note that e to the whatever can't be 0. So we can actually divide that out. So you're left with 2x equals 0 or 2y equals 0. And collectively, they imply a single critical point, which is the origin, right? So the origin's the only critical point we got in this problem, right? Which is nice because we don't have to go on a whole bunch of long repetitive calculations. The next thing we got to do is we got to calculate the Hessian. Now the Hessian is a matrix of second partial derivatives, right? So it's got the coordinates, the non-mixed ones, they're just the pure double ones down the main diagonal, and it's got the mixed derivatives on the off diagonal, right? In this case, a Gaussian surface is smooth, it's continuous, it's a beautiful function. It's not going to have any discontinuities in the first derivative. So we know that the mixed partials are going to be the same everywhere. So we only have to evaluate one of these. We don't have to evaluate both of them, both of the mixed derivatives in the different directions. So second derivative of this, we got to use our product rule. So differentiate the first one, leave the second part alone. We get 2x e to the minus x squared minus y squared. Differentiate the second bit, leave the first bit alone. Now we've got to use function of a function rule. So the e stays the same. But when we differentiate the argument of the e, we're going to get a minus. We're going to get another 2x, like so. Right, let's cheat and do the second derivative of y by essentially just pattern matching. Oh, hang on, I had to differentiate that one. Differentiate the first part, right? That's 2x. There shouldn't have been an x there. That was a typing error. A handwritten typing error. Okay. The last thing we've got to do is we've now got to do the mixed derivative. So take y, for example, differentiate with respect to x. That 2y is a constant, so we're just going to be doing function of a function rule. Get minus 4x. There's a y there now out the front as well. E to the minus x squared minus y squared. Alrighty, now we can build our Hessian. Okay, that's our Hessian matrix. We've got to evaluate this at our critical points. That's the origin. And when we evaluate this thing at the origin, well, it gets pretty simple. Now we have to take the trace and determinant of this thing. Again, it's trivial. The determinant, we multiply the diagonal terms and subtract the product of the off-diagonal terms. So we have a positive determinant. That means that we have either a minimum or a maximum. And now we work out the trace. The trace is positive. That means that we have a minimum, right? We've got this kind of behavior going on. Right, and if you're familiar with what a Gaussian looks like, you'd realize that it looks like this in cross-section in, say, the XZ plane, or the XF plane, and in the FY plane it's gonna pretty much look the same as well. So it's you got this bell-shaped curve. Because it's negative, it's under the axis, so it's clearly going to be a local minimum. Alrighty, we're done.